What are the benefits of continuously adjusting parameters using the Newton-Raphson method, and how does this help in achieving a more accurate structural model? How does the modified structural model obtained from this process match the actual one? And why is this comparison crucial in the context of material characterization? What are the key differences between the Pauli and Liebel methods in terms of their approach to refining diffraction peaks and optimizing structural models, and how do these differences affect the results of XRD analysis? How do the advantages and disadvantages of these three refinement methods, Pauli, Liebel, and Rietveld, compare, and what factors should researchers consider when choosing a method for their specific material analysis? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? Why is it important to have a comparison table of these methods, and how can such a table help in selecting the most suitable method based on the material and research goals? What specific applications or materials benefit from the use of the Pauli, Liebel, or Rietveld refinement methods, and how do these methods contribute to advancing research in fields like battery technology, nanomaterials, or material science? How does the continuous refinement and optimization of XRD data using these methods lead to more accurate predictions and better material designs in various scientific and industrial applications? What are the main advantages and disadvantages of the Pauli method in X-ray diffraction, XRD, analysis, and how does it compare to the Liebel and Rietveld methods in terms of computational requirements and refinement parameters? What are the benefits of the Pauli method, such as not requiring a crystal structure model of the material, and how does this make it a simpler option for certain types of material analysis? What challenges does the Pauli method face, particularly with the number of refinement parameters required and its computational intensity, and how do these challenges affect its use in more complex analyses? In what way does the Liebel method address some of the limitations of the Pauli method, such as offering faster convergence and fewer calculations, and how does this impact its application in practical scenarios? What makes the Liebel method particularly advantageous in terms of refinement speed, and how does it allow for accurate results with less computational effort? What are the potential drawbacks of the Liebel method, especially when dealing with similar diffraction peaks, and how does it necessitate final judgment for more accurate interpretation? How does the Rietveld method differ from both the Pauli and Liebel methods, and why is it considered to have a wide range of applications, especially for determining lattice parameters and analyzing phase composition more precisely?